Today is very important lecture, which is about change of basis. Okay, let me tell you. So essentially, it's obvious that, for example, let us suppose that we have a basis which is in R2, this one, right? And we have standard natural basis in R2. Then let's say that I have C1, C2, which gives me a representation of vector V with respect to the basis B, right? And I have x1, x2, which is a representation of, pay attention, the same vector V with respect to the basis, the natural basis in R2. Okay, how to find C1, C2 if you know x1, x2, and vice versa? How to find C1, C2 if you know x1, x2? Okay, now when we studied inverse matrices, so I can show you the direct way how to do this. So, okay, for example, so pay attention, these are representations. So this is a representation with respect to the E2 of vector B1 of the matrix of the B1, B2. And this is a representation with respect to E2 of the second vector of the basis, right? Because usually when we write something just like that, not listing the basis, we mean that this is representation with respect to the natural basis. Okay, now what does it mean? So pay attention. So we had vector B, right? V, sorry, and then C1, C2 was C1 on B1 plus C2 on B2, right? So just coordinates with respect to the basis B. But also, of course, just remember that usually we write it vectors of the natural basis E1, E2. So what does it mean that we have x1, x2? So it means x1 on E1, right? Plus x2 on E2, right? So x1, x2 are coordinates of the vector V with respect to the natural basis, right? Or basis of E1, E2, right? Are there any questions for now? Because this is extremely important topic, and I promise you that a problem like that will be in your exam. Any questions? Okay, great. Now, how can I write these? So it's C1 on the, if I want to represent it with respect to the representation of V with respect to E2, for example. So I can write it like that, C1, C2, and then I need to use representations of vector B1 and B2 with respect to the natural basis, which are given, right? Just this. From the other point of view, what is that? It's x1, 1, 0, plus x2, 0, 1, right? Have a look. How can I write it? I can write it as 1, 1, 1, negative 1, C1, C2 equals to. Here, I will leave these vectors as is. And here is x1, x2. Okay, so as a result, if you want, so is it clear how I got this?
It's clear.
Okay. Now, from here, I can immediately do the following. So first of all, these vectors, these matrices, they contain the representation of basis vectors, right? As columns. But because basis vectors are linearly independent, so we are getting all columns linearly independent. This is matrix of the full rank or non-singular matrix, right? So non-singular matrix, it means that it's invertible. It means that from here, I can write C1, C2 equals to 1, 1, 1, negative 1 inverse on this, right? So could you tell me? So it was, by the way, part of the last homework. If I have matrix 2 by 2 matrix, what will be the inverse one? So we have proved. Yes. Could you continue?
Minus A1 times A21.
Okay. And what is here?
A22 for the first element.
And negative A21, negative A12, right?
Correct.
So idea is the following, that have a look. Here we have expression, which is product of the element on the diagonal minus product of the element of diagonal, right? So it's so-called determinant of this matrix, 2 by 2 matrix, but we will study them later. We really start studying them today. Okay, so we have this. Okay, now here we just switch the elements on the diagonal and change sign for the elements of diagonal. This is how to remember how to find inverse matrix. Okay, 1, 1, 1, negative 1. Okay, could you tell me what it will be? Negative 1 minus 1, right? Right or not?
Right.
Right.
Okay, and what will be here?
Negative 1.
1, right? Switching elements on the main diagonal. Oh, sorry, yeah, of course, negative 1 inverse. And changing the sign of the elements of diagonal, right? Elements. So this is 1/2, negative 1/2. So I will put the negative side sign inside, and this will be 1, 1, 1, negative 1, right? Let us check. 1/2, 1, 1, 1, negative 1, 1, 1, 1, negative 1, which is 1/2, 2, 0, 0 to identity matrix as expected, right? So if you have time and if you're got in trouble, so it's always good idea to check whether you found your inverse matrix right. Just multiply it on the original one. You're supposed to get identity matrix by definition of inverse matrix, right? Okay, so the result. Yeah, by the way, because here we have identity matrix, we can just omit it because it doesn't change the vector. So as a result, this will be okay.
I was just wondering, so is doing the multiplying by the inverse of the matrix kind of like dividing by that matrix?
Yeah, you see, there is no division, right? So if we have ax equals to b, right, equation, right, for example, like that. So for scalar equation, right, then we can do the following. X is b divided by a, or you can write a to the power -1 on b, right? If a is not equal to 0, right? Right or not?
Yeah, correct.
Now you have ax equals to b, right? So how you can find x? You can multiply by a inverse both sides, right? And then what you will get? This, by definition of inverse matrix, is identity matrix, right? So it doesn't change the vector. Of course, you can do this only for square matrices, right? So because right now we are talking only about the inverses, the left and right inverses. So that's it. So then what you're getting x is a inverse b, right? Just like that. So it's kind of like dividing by the matrix, but it's not really division. First of all, because multiplication by the matrix is not commutative. And second, because if here you could exchange the order, right? Here you cannot exchange the order because multiplication will not be defined. So this is why here it's important from what side you are multiplying by your inverse matrix, right? Because, for example, b a inverse, take into account that b is n by 1 and this is n by n, so not compatible, right? So this is not defined. So this is why what I'm saying, that it's not exactly division, but it's similar to that. It's as close analog to the division as possible. But you need to remember that you need to keep track on from what side you multiply by the matrix, right? Because have a look. Ax equals to b, right? You need, in order to get rid of a, you need to get a inverse a, right? So this will be identity matrix. It means that you need to multiply both sides from the left by the inverse matrix. Is it clear or not?
Yeah, it's clear. So you multiply it on both sides of the equation by the left.
Yeah, so for example, you have these and you want to solve for matrix A. How would you do this? So you want to solve for that, and you know, so these B and C are known matrices.
Then I'm multiply by B inverse on in between A and B on the left side of
you cannot multiply in between, right? So you cannot just insert it in between, but you can multiply by B inverse from the right, right?
So then do you have to have a different inverse? Because aren't the left inverse and the right inverse different?
So first of all, when we denote inverse of A as A like that, right? We are talking about left and right inverse. It was in the definition. So essentially, it means that A inverse A equals to identity matrix, and A inverse equals to identity matrix. So we are not talking about left and right, left separately and right separately inverses, because this notation is defined only for square matrices. Just have a look at the definition. So, okay.
Yeah, that makes sense.
Yeah, so now you multiply. So you see, you cannot, so if you have AB, right? So you cannot just include here B inverse, because you had it equal to C. Where you should include your B inverse? You cannot put it inside of C, right? Right? You cannot do this. But what you can do, you can multiply from the left by A inverse, for example. And then this will be identity matrix, which doesn't change anything. So you solve for B. Or you can multiply from the right by B inverse, right? And then this is identity matrix, and then you solved for A, right? So here, pay attention that here, for example, this is not equal to CA inverse, right? And this is not equal to B inverse C. It's important because have a look what will happen with your original expression. If you, for example, multiply from the A, multiply C from the right by A inverse. So this is not B at all, right? It's not the same, because you cannot bring together this matrix A and A inverse, because matrix multiplication is not commutative. So you cannot just exchange B and A inverse, for example, or A and B inverse. Not commutative. Cannot do this. Cannot do this. Is it clear or not?
That's clear, yeah.
Any questions? So you need to track where is your matrix and from what side you need to multiply in order, for example, here, in order to get rid of A here to express X, right? I needed to multiply from the left. But here, in order to get rid of B, I needed to multiply from the right. Clear or not?
But usually you multiply by the left. So you usually multiply
No,
by the left.
there is no such thing as usual in this case, you see, because if you are talking, for example, here, yeah, I mean, here, when we are talking about change of basis, like here, for example, right? In this case, yes, you multiply from the left. I agree with you. Why? Because here, multiplication from the right would not be defined at all. But in general, you can have a matrix equation, and then you will decide, so depending on this matrix equation, for example, X, yeah, for example, A B, and it's equal to C. How to solve for X if you know A, B, and C?
If you know A, B, and C, and you A, B, and C, and you want to get X,
Yeah.
would you first then have to get rid of either A and B so you can multiply by the left or by the right to get X?
You see, not by the right, not by the left, from the right. So you're multiplying from here, right? So, and you're getting A inverse A, right? And here you're getting A inverse C. And then also you need to get rid of B. So you have to multiply by B inverse from the right, right? So this will give you identity matrix, this identity matrix, right? So you can just neglect it, right? So it doesn't change. And here you got this. Is it clear or not?
Yeah, that's clear. Yeah.
Okay, perfect. So now, once again, so we had this, we were able to find how to represent, how to find the representation of the vector V with respect to this new basis, this one, if we know representation with respect to the natural basis. But of course, these, so here you see I was keeping this 1, 0, 0, 1, although I could just immediately write this, right? So x1, x2. So, but this shows how to do this in an arbitrary way. For example, once again, let me consider basis B, which is the same 1, 1, 1, negative 1, right? And let me consider basis C, which is, no, C is not good. So D, which is, let's say, I will use natural basis, but just exchange the order of the vectors. Pay attention, this is not natural basis anymore because order of the vectors is different, right? So if here you had x1, x2 representation, then here it will be x2, x1. So it's different, right? So, but I don't want to use these. So I will just do this in an arbitrary way. So pay attention that both these bases, so what are these and that? These are representations with respect to natural basis. So it means that if you have your vector V, so, and this is C1, B1 plus C2, B2. And from the other point of view, so if this is D1, this is D2, right? So then let us say that you have alpha 1 D1 plus alpha 2 D2, right? So then you can say that representation with respect to the natural basis of vector V will be, so it will be something, right? Yeah, but here you will get C1 1 1 plus C2 1 negative 1. From the other point of view, here you will get alpha 1 0 1 plus alpha 2 1 0. or you can write it as 1, 1. Pay attention, this representation of the first vector goes to the first column. 1, negative 1. Representation of the second vector goes to the second column. C1, C2. Just because of mechanics of multiplication of matrix on the vector. And this has to be equal to, so this, the same representation with respect to the natural basis. Why? Because these vectors are represented with respect to the natural basis, right? And here we have 0, 1, 1, 0, alpha
Professor?
1, alpha 2. Yes.
I just kind of have a silly question.
There
So
are no silly questions. There are unasked questions, and which left you with misunderstanding. So go ahead.
I understand like what we're doing, but when you say that these vectors are with respect to E2, the natural basis, like B and D, is that just because they're two entry vectors? Like it's a two entries in a column vector. That's why it's
Yes,
respect to E2?
we all the time we are working with in R2, right? So usually, so you need to represent your vectors in some form, right? So usually people use natural basis because it's simple. But there are cases when different bases are useful, and we will see. So essentially, all solution of ODEs, for example, ordinary differential equations. So it's switching to the basis where solution is easy to get. So finding some special basis. So as a result, we need to know how to switch between bases. So, and then essentially here, but it's easier just if you are given the vector. So, and we will consider polynomials just a little bit later. So if you are given the vectors, so it's usually in general, I mean, usually it's easier to represent them with respect to the natural basis. This is exactly why this basis is called natural. So it's the basis which comes to mind first. So and this is why usually basis vectors, so these vectors, for example, B1 and B2, so this is B1, this is B2. So usually, so they are given with respect to natural basis. But it's not necessary. So you could always say that, okay, let us say that this is a representation with respect to some other basis. But then the only thing is that in order to be compatible, you need to represent vectors of these other bases, I mean the basis D, with respect to the same basis as well. Because you see here, I'm saying that, okay, let us represent our vector V with respect to, let's say, natural basis, right? But then this is nothing else but representation with respect to the same natural basis of B1, right? And this is nothing else but representation with respect to the natural basis of B2, right? And this is nothing else but representation with respect to the natural basis of D1, right? And this is nothing else but representation with respect to the natural basis of D2, right? So you see, these column vectors, they correspond to representation with respect to the same basis. This is why I can make this equation, right? Because these are coordinates with respect to the same basis.
Okay, thank you, Professor. That helped.
We shall do example with polynomials, and then probably there it will be even clearer. So, okay, here. Now, I don't really need, so pay attention, I don't really need to switch first to the natural basis. I can just say that they are equal to each other. This is the only thing why I have it. So I just need to remember that this is a representation of the same basis V, the same basis V, vector V, sorry, vector V. So this is why they have to be equal to each other. Okay, now I have 1, 1, 1, negative 1, C1, C2 equals to 0, 1, 1, 0, alpha 1, alpha 2. So vector C, vector alpha. So could you tell me how to get vector alpha if I know vector C?
You multiply the inverse of 1, 1, 1, negative 1, or B, you multiply it the right side of the equation by the inverse of B to get C. Oh, to get alpha. Oh, oops, sorry. Yeah.
But I mean, idea is right. Just you
Just the wrong
express
thing.
C instead of alpha, right? So now, if I want C, exactly as you said, I need to multiply by B inverse from the left, right? Then these will be eliminated. It will be identity matrix, and here I will get this, right? So this is what you need to remember. Essentially, you express your vectors of your both bases. You express them with respect to some convenient basis like that, like column vectors, construct matrices, and then these matrices multiplied on the coordinates vectors, this and that. So they have to give you representation, because it's just representation of some vector V, right? You need to remember that this is just some vector V, and it's the same vector. So they have to be equal. They have to be equal to each other. And then from here, from this equation, BC equals to D alpha, right? So you immediately can get either this or that, multiplying by corresponding inverse matrix from the left. Is it clear or not?
Yes, I have a question. So
Go ahead.
what are we changing from and then to? Like the alpha is okay.
So here C, vector C, right? This C1, C2, these are coordinates with respect to the basis B, right?
Right.
Coordinates of the vector V, pay attention, V, right?
Right.
So you know coordinates with respect to the basis B. Now you want to find what will be coordinates of the same vector, but with respect to the basis D. So which means that you're trying to find alpha 1 and alpha 2. So essentially problems is formulated like that. Suppose you know C1, C2, what will be alpha 1, alpha 2? And I solved it here. I multiplied by matrix D from the left, D inverse from the left. And now if I will be able to find these, so I just multiply this matrix, right? The product of these two matrices on any C, and I will get immediately what will be the representation with respect to the basis D. I mean alpha 1, alpha 2, right?
Okay, for sure, yes, thank you.
Okay, could you tell me what will be D inverse? Anybody?
One over -1?
Yes, 0, 0 minus 1 on 1, right? So because this minus that. Okay, and here what I will get?
0, -1, -1, 0.
Exactly. Which will give me just this, right?
Right.
So as a result, D inverse B will be 0, 1, 1, 0. Multiplied on B is 1, 1, 1, negative 1. Okay, what it will be? First row, could you tell me? This on that, right?
1, negative 1.
Mm-hmm. Go ahead. Second row.
I'm thinking.
Oh, come on. So 1 on 1, 0 on 1, right? So yeah, go ahead, somebody.
So it'd be 1 and then
1.
Yep, 1 again. Because the last one is this multiplied on that, right? 1 on 1, 0 on negative 1, right? So this change of basis matrix or transition matrix from B to D, right? So from basis B to basis D, right? So we are finding essentially, so what is that? It's a representation with respect to the basis B of the vector V, right? And what is that? It's a representation with respect to the basis D of the same vector V, right? Clear or not?
It's clear.
clear.
So this is transition matrix. So if I've asked you to find transition matrix from respect to between two bases, right? So pay attention, from basis B to basis D. So essentially, my recommendation, please do not ever try to remember, okay, then this is like that and so on. So believe me, in 50% of the cases, you will be wrong. Just remember that, okay, I have B, so just column vectors representation of my basis, right? And then D, let's say on alpha, column vectors representation of a different basis. Then that's it. So from here, whether I'm telling you, okay, I want to find transition matrix from basis D, from D to B. It means that from D, right? It means that you know alpha and you want to find C, right? So then how you do this? C will be B inverse D alpha, right? This is your transition matrix from D to B. Clear or not? Just remember this, that it's different representations with respect to different bases, but of the same vector. This is the most important part. For example, let us consider the following 1 plus x, x. So this will be my basis B1. And I will consider B2, which is 1 to x. Just like that. Okay. Or no, don't want to have 1 here. Want to have something crazy. Let's say 7. So you can check that any of so B1 and B2 they are bases in P1. space of polynomial, space of linear polynomials. Now, I want to find transition matrix. What is transition matrix from, let's say, B2 to B1? So what it means? It means that you know, let's say, so you have a vector V. So you can represent it as, let's say, x1 multiplied on 7 plus x2 multiplied on 2x. Vectors of the basis, right? So these and these are coordinates with respect to B2. From the other point of view, you can write it as y1 on 1 plus x plus y2 on x. So these are coordinates with respect to B1, right? So what to do? You can say that, okay, I can represent this vector V, for example, with respect to the standard basis, right? So it will be some V1, V2, right? Representation with respect to the standard basis of V, right? What is standard basis? Is 1x, right? Standard.
Professor, what's the notation for standard basis of polynomials? Still E2 or?
Yeah, you can use it too, but usually, I mean, I don't know what is the notation. I don't remember, frankly speaking. So it's just, it doesn't matter. So we just know that standard basis is 1x, x squared, x cubed, and so on, depending on what particular polynomials you are considering. Okay. Now, so this is why. So I want to represent now this vector with respect to the standard basis. Could you tell me what will be the representation? How can you write it? It's
Maybe
1,
1,
1. Like that, right?
Yeah.
So it's 1, 1. Okay. Plus y2. What will be the representation of this? It's 0 on 1 plus 1 on x, right? So vectors of the standard basis and corresponding coordinates. Is it clear or not? Any questions? Okay, so this is, so this vector, what is the representation with respect to the standard basis?
7, 0.
Right. This vector, what is the representation of, with respect to the standard basis?
0,
0.
2.
Thank you, both of you. So, okay, so it means that, how can I write it? 1, 1, 0, 1, y1, y2 equals, I don't need this intermediate vector, right? So I can just write 7, 0, 0, 2, x1, x2. Clear or not? So, is it clear or not what I've just done?
It's clear.
Okay, now I need to find transition matrix from B2 to B1, which means that I know coordinates with respect to B2 axis. I know them. And I need to find y1, y2. So how can I get y1, y2 from this equation?
You have to take the left inverse of the matrix 1, 0, 1, 1.
Yes, but I mean, because this matrix is non-singular, it's a representation of the basis, right? And by a non-singular matrix, so you can say left inverse or right inverse, doesn't matter. So you just take inverse, because inverse will be the same for left and right. And but we need to multiply from the left. This is exactly exactly true. So I believe you meant that we need to multiply from the left, right, by the inverse of this matrix.
Yeah, because it's
Yeah.
on the side.
Yeah. Okay, so this will be my transition matrix T, which will be 1 over 1 minus 0, 1, 1, negative 1, 0, multiplied on 7, 2. So this is just 1. So we are getting 7, 0, negative 7, 2, right? Right or not?
Yes, that's right.
So this is the answer. So is it clear why we need to switch to the standard basis? Just, is it clear or not?
Yes, it makes more sense why you have to do that.
Yeah, because it's just easier to represent these arbitrary vectors of this arbitrary basis with respect to the standard one, right? So it's just easier. But once again, it's not necessary. You just have to stay in the same basis. For example, you can, it's a little bit crazy because it's more complex, but still, for example, you can consider not standard basis, but for example, basis instead it will be x1, for example. So you see, I exchanged the order of vectors, right? So, and then correspondingly, pay attention. Coordinates, these coordinates and these coordinates stay the same. Just representation of the basis vectors, these things will change, right? But pay attention that coordinates have to stay the same. From the other point of view, because you're working in the same basis, right? The representation is unique, so no problem whatsoever. Have a look. So this is what you will get. And here will be 0, 7, 2, 0. So if you like, you can try to find transition matrix. It's again 1. Yes.
Professor?
Yeah.
Why would the matrix multiplied by the coordinates y stay the same if the basis is changed?
No, matrices will change. But you
Yeah,
see,
I'm talking about
this,
the matrix.
yeah, this coordinate, yeah, probably made a mistake. Wait a little bit. Yeah, here. So when I exchange like that, the basis, so we switch the coordinates. Yeah, like that. It will be like that here.
Okay.
So
Thank
idea is the following, that these things, right? They are coming y1, y2. They are coming just from here, right? they are not knowing with respect to what basis we will be representing in a matrix form the basis vectors in the polynomials vector space, right? They do not know about that. So as a result, of course, these coordinates, they are introduced for the polynomials, right? For the basis in the space of polynomials. So when we are changing the representation matrix, so here, so only these things can change. And this is exactly what happens. So you see, we had x, right? Before it was second coordinate, it was 0, 1, right? So 0, 1. Now, because we are considering x1 basis, right? Now it's 1, 0. So, and now we can try to find transition basis, transition matrix. So it will be 0, negative 1, 0, 1, negative 1, negative 1. So it's inverse of that, right? Exactly as before. So please. And here we have 0, 2, 7, 0, this. So it will be, okay, first of all, we can get rid of this and make change sign here. And then we will get the following. It will be 7, 0, negative 7, 2. So obviously, as it's supposed to be, transition matrix for the coordinates with respect to some basis. For this transition matrix, it shouldn't change when you with respect because you change the representation in the matrix form, right? So you just change the representation, so you change the basis with respect to which you represent your basis vectors. But coordinates with respect to this basis have to stay the same, obviously. This is why for transition matrix, it doesn't matter this intermediate basis which you use to represent your basis vectors through these matrices, right? Is it clear or not?
Is this always true?
Yes, of course, because once again, this is what is real. 7 and 2x, 1 plus x and x, this is what is real. These things, this 7, 0, 0, 2, right? These things, they are just representations of our basis vectors, right? So essentially, we are creating isomorphism between P2 and R2. But how we create this isomorphism? It depends on, for example, what basis we will choose to represent, right? But of course, these coordinates, they do not supposed to feel that, right? Because they are coming from here. They are coming from real coordinates in the space of polynomials. They do not care how you represent with respect to what basis you represent your polynomials when you're trying to switch them to two-dimensional column vectors, right? It doesn't matter for them. Is it clear or not? Or
Yes, thank you.
mm-hmm. So this is why transition matrix will stay the same, regardless of what representation, common representation basis you use, either like here or like here. like here.
So do we have to also change the second basis if we?
Yes, of course. This is what I'm saying all the time. When you do this representation, right? This representation. So you have to represent the basis vectors with respect to exactly the same basis. You see, here I use standard basis. Why? Because you essentially trying to equate representations of the vector expressed through different bases. So if you're trying to represent, like here, your vector with respect to the standard basis, then on the left and on the right, these and these, and these, you need to use here the same basis vector in order to get these column vectors, right? I mean, not the same basis in order to get these column vectors. Here we used standard basis. If instead we will be using these bases, then obviously when I'm switching here to the vector, so pay attention. I'm getting these, yes, it coincides, but already this vector is different. So representation is different. But obviously, so you see here, so 7 before was 7, 0, right? 7 before was 7 multiplied on 1 plus 0 multiplied on x for the standard basis. But now it's 0 multiplied on x plus 7 multiplied on 1 for these bases, right? And this is exactly why 7, 0, this one, is changed to 0, 7, right? Because you remember when we introduced the basis, right? The concept of basis, the definition, I told that it's ordered minimal spanning set. And the order was important exactly because you need to know to what vector, on which vector you need to multiply the first coordinate, on which vector you need to multiply the second coordinate, and so on. Is it clear or not?
It's clear. You have p equals. Is that to reinforce that this is a polynomial?
Where p equals?
Lower. Further down, when you have the solution.
No, where? Here?
On the left, is that a letter?
It's t.
Oh, t. Okay, cool.
It's transition matrix.
Okay, great. Is that also
Yeah,
because it's rotating it?
Okay, so I don't want to talk about rotation right now. So it's just a switch of bases, change of bases. Okay, so this is the only thing which matters here.
Okay, one more thing. Should we think about it in terms of the polynomial, or are we satisfied with the matrix that we have now as a solution?
You see, this matrix, because we are working with coordinates, right? So essentially, what this matrix tells us, it tells us the following, that if you know your x1, x2, which are coordinates in the space of polynomials, right? In order to get, with respect to the basis B2, then in order to find coordinates with respect to the basis B1, you need to multiply the column vector of coordinates 7, 0, negative 7, 2, right? You need to multiply it by this matrix, and then you will get y1, y2. Have a look. So y1 multiplied on, so the first vector was 1 plus x plus y2 multiplied, second vector was x, right? Right. So it's the same as x1 multiplied on 7 plus x2 multiplied on, what was that, 2x. So, for example, if this was 3756, right? Then I know that 37 multiplied by 7 plus 56 multiplied by 2x will be equal to, I multiplied 37, 56 by this matrix. I'm getting corresponding y1, y2, and multiply on these basis vectors, and I'm getting the result. Is it clear or not?
Yes.
So these are coordinates. So y1, y2, and x1, x2, it's just convenient for us to represent them as column vectors, right? But really, these are coordinates in the polynomial space, or space of first degree polynomials. Is it clear or not?
So what is it doing with these vectors? So you're saying that it's a transformation, taking it from one place to another.
One basis to another.
Okay, one.
But vector is the same. Pay attention that this is vector v. Its representation with respect to one basis, and this is the same vector represented with the different basis. It's the same vector. Vector is an element of the vector space, right? I can use any basis to represent the same vector with, to use representation of some vector, right? So I usually use some basis. I don't know any other approach. So as a result, so I need to be able to switch between two different bases of representation of the same vector. And this is exactly how to do this. So you find this transition matrix, create a column vector of coordinates in the one basis, multiply by transition vector, and you are getting column vector of coordinates in another basis.
Clear.
Okay, perfect. So now, I prefer this way of explanation, which is different from what is written in the book. If you like, please read the book. So they use this identity map representations and so on and so on. So now, you remember we were considering matrix representations with respect to of homomorphisms. With respect to pair of bases. So we were saying that, okay, if I have H, which maps V into W, and here I have basis B, and here I have basis D. Then I can write M, which is representation of H, my homomorphism, with respect to the bases B and D. Okay, now let us talk about isomorphisms, but it's not really necessary. Homomorphisms. Okay, now, for example, so essentially you have the following. You have V and correspondingly basis B. Now you have H and you have H capital, which is the representation of, here you have basis D. And you have H capital, which is a matrix representation of our homomorphism, right, with respect to this basis. Okay, now question is the following. If we have B prime, different bases in V, and different bases in W, homomorphism, because it's linear map is the same, but obviously we will have different representation, right? Because it's a representation of homomorphism B prime, D prime, right? With respect to different bases. How to find it? So what it means that first you write the, so if you know coordinates here, and then you want to find coordinates with respect to these bases here, right? So if here you had, let's say, X vector of coordinates, and here you had Y vector of coordinates. So idea is the following, that Y result here was H multiplied on X, right? H, yeah, H, which is this. So is it clear or not?
It's clear.
Okay, here I have X prime, and here I have Y prime, right? So it was, in order to find Y prime, I need to use H prime on X prime, right? Like that. Now, the question is that suppose this is known. How to find H prime knowing H? Okay, this is how. Pay attention. If you know bases B prime and B, you can find transition matrix, right? For example, from B prime to B, transition matrix from B prime to B, right? Then you already know how to apply your homomorphism to coordinates with respect to the basis B prime. How? You just first switch using transition matrix from B prime to B. So this already will be X, right? Coordinates with respect to the basis B. Then now you can apply your homomorphism, right? Like that. The only problem is that you will get coordinates with respect to the basis D. You will get Y's here. So what you need to do, you need to switch from D to D prime. You need to find transition matrix from D to D prime, like that. And this will already be because this will give you just y, and now you already have y prime. So this is nothing else because representation is unique with respect to the basis. This is nothing else but h prime. So h prime is transition from b prime to b, then your known homomorphism matrix representation, then transition from d to d prime. Is it clear or not? You can also say that this is nothing else but, okay, you can use that equation. So you can use this.
Professor.
Mm-hmm.
So for the B transition matrix, we find it from B prime to B, but for the
Yeah. Let me show it.
Okay.
So you see here, first we need to switch from B prime to here, where we know how to apply our homomorphism because we know this, right? And then, but we get result in here, right? So we get y. So, and then we need to switch from this basis d to basis d prime, right? So in other words, so we are trying to find this thing, right? Okay, but I know how to apply homomorphism only to, and I know how to apply these to correspondingly. So I know this. No. This is what we are trying to find. So then I will do the following. Here, I will say that, okay, but this will be transition matrix. So y prime multiplied by transition matrix from B prime to B, right? Have a look. B prime here, B here. So I know how to get to y if I know y prime, right? Then here, so I know how to apply homomorphism, but I need to get from h prime to h, from x prime to x, sorry. So this, how to get from x prime to x. So this, oh, sorry. Yeah, by the way, y is d. Yeah, because y is here on this side. Y and y prime here. So I know how to switch from x prime to x. So this will be transition matrix from B prime to B on x prime. So this is my x, right? And this is nothing else, once again, but B. But now all I need to do, I need to multiply from the left by T inverse D prime D, H T B prime B X this, right? But this is nothing else but transition matrix from D to D prime, right? Have a look, because essentially you had T D prime D Y prime was equal to Y. So now you need to solve this equation with respect to Y prime. You just multiply by the inverse from the left. Yeah, like that. But what is this? It's this will be transition matrix from this is representation of the vector with respect to the D, right? And this is representation of the vector with respect to D prime. So this, then this is nothing else but T from D to D prime. That's it, which is exactly the same formula. Have a look. This, taken into account this equality, is exactly this formula.